In this segment of video, we're going to show you how we do anion chromatography to strip out iron. Iron's a typical component of quartz, and if we don't remove it from our samples, the samples will not run as well on the accelerator, and the cation columns afterwards may not perform as well. At the beginning of the process, we need to make sure that all the cations in the sample are bound with chloride ion. Therefore, we add and evaporate several milliliters of strong HCl, a step which can take a couple hours. This displaces the perchlorate that is associated with those cations from the perchloric dry down. We have several different equipment setups. We start with 6-normal hydrochloric acid in a clean Teflon squirt bottle. There's a beaker into which we empty some of that acid, and then a variable pipette that we use to remove the acid from that beaker and place it in the large sample beakers, which are off on the right. That hot plate has the beakers in their standard order, and inside each one of those is a little pellet of material that's left after the perchloric acid dry down. We have transfer pipettes that we'll use to move that material out of the large beakers and into the labeled 15 ml test tubes that you see here. To prepare the samples, we dilute them in 5 ml of 6-normal hydrochloric acid. They need to be in that strong acid so the column resin will separate iron from the other cations. After diluting the samples, we centrifuge them to remove any precipitate that forms. The precipitate is some, but not all, of the titanium in the sample. That titanium was oxidized by the perchloric acid during those 4 perchloric acid fumings. We'll remove the rest of the titanium in the next video. Column chromatography relies on a vertical column of organic resin. We build these columns at UVM. They have both top and bottom frits to protect the resin, and we reuse them. The fluids flow down through and interact with this resin. In this method, we complex iron with chloride, which creates an ionic complex with a net negative charge. Even though iron itself is a cation, here it is behaving as an anion because it is in the chlorine complex. This negatively charged iron chloride complex then binds to the positive sites on the column resin. The aluminum and beryllium are not retained and flow directly through the resin. We'll exploit this behavior, the binding to iron, so that the resin captures all of the iron from our samples. We need to remove this to make sure that the resulting beryllium and aluminum are pure and will run well in the accelerator. Second equipment setup. So the first thing that we see here are the labeled 15 ml tubes. Those have the samples in them. Then we have the anion columns on a rack, and they're labeled A through F and then G through L. We have the 6-normal hydrochloric acid that we're going to use to elute the samples through the column. And then we have the 1.2 normal hydrochloric acid that we're going to use to clean the columns afterwards. The sample beakers are here ready to receive the samples from underneath the columns, and then they will be dried off on this hot plate. To prepare the columns, we first clean them in weak HCl, 1.2, that flushes all the cations off, and then we condition them in the strong 6-normal HCl. Once they're prepared and the columns are drained, we load the sample onto the column by pipetting it using the disposable pipette dedicated to each sample. It's critical we pipette carefully and leave behind any of the precipitate at the bottom of those centrifuge tubes. Otherwise, those solids will plug the anion column. As the sample percolates down through the column resin, the iron binds onto the resin and stays behind. The other cations pass through into the beakers below, and you can notice that the iron-rich solutions at the top of the column are yellow, and the solutions dripping out of the bottom are clear because that iron chloride's been removed. In order to make sure all of our non-iron cations have been completely passed through the column, we follow the sample with additional 6-normal HCl to flush out the columns. At this point, we have all our samples done. They go on the hot plate. Then, before we evaporate the samples overnight on the hot plate in those small beakers, we add a small amount of sulfuric acid so the sample will not go to dryness and we might lose it from static. We add just the right amount of sulfuric acid to properly prepare the samples for the next set of columns methods that we'll execute the following day. To clean the columns, we flush them with 1.2 normal HCl to release all the iron they stored, and we put that to acid waste, and then we flush them and store them with clean deionized water. We do anion column chromatography to remove iron that is present in our quartz from the sample. We start by redissolving the pellet that's left after perchloric acid treatment in strong hydrochloric acid, and then we dry that acid off to make sure we've converted what's left to a chloride form. We bring that material up in 6-normal hydrochloric acid. We then centrifuge, which allows us to remove any solids that might plug the anion column. The solids are mostly oxidized titanium. We use strong hydrochloric acid to make an iron chloride complex that clings tightly to the column resin. That acid carries beryllium and aluminum through the column and into the beaker below. Once the beaker's been removed, we then clean the columns with dilute hydrochloric acid, which removes the iron, and then we rinse the column with water, fill it back with water, and store it. We add a little bit of sulfuric acid to each of the samples and evaporate the remaining water and hydrochloric acid to prepare for cation columns.